Chapter 4. Image Fundamentals and Representations. Learning Objectives. In this chapter, the users would learn the following aspects of image fundamentals and representations: color science, color models, color palettes, dithering, 2D graphics, image compression and file formats: GIF, JPEG, JPEG 2000, PNG, TIFF, EXIF, PS, PDF. Basic image processing, use of image editing software, white balance correction, dynamic range correction, gamma correction, photo retouching. Introduction. At the end of this session, you will be able to work out your graphical approach by planning your approach, organizing your tools, and configuring your computer workspace. Differentiate among bitmap, vector, and 3D images and describe the capabilities and limitations of all three. Describe the use of colors and palettes in multimedia. Cite the various image file types used in multimedia. Importance of visuals. Multimedia on a computer screen is a composite of elements: text, symbols, photograph-like bitmaps, vector-drawn graphics, three-dimensional renderings, distinctive buttons to click, and windows of motion video. It may be a very colorful screen with gentle pastel washes of mauve and puce, or it may be brutally primary with splashes of Crayola red and blue and yellow and green. It might be stark black and white, full of sharp angles, or softened with gray-scale blends and anti-aliasing. It may be elegant or by design, not. The computer screen is where the action is. Color science. At the beginning of a project, the screen is a blank canvas, ready for you, the multimedia designer, to express your craft. The screen will change again and again during the course of your project as you experiment, as you stretch and reshape elements, draw new objects and throw out old ones, and test various colors and effects, creating the vehicle for your message. Indeed, many multimedia designers are known to experience a mild shiver when they pull down the new menu and draw their first colors onto a fresh screen. Just so. This screen represents a powerful and seductive avenue for channeling creativity. The basic steps in designing the multimedia project are: plan your approach, organize your tools, configure your workspace. Plan your approach. Whether you use templates and ready-made screens provided by your authoring system, clip art, or objects crafted by others, or even if you simply clone the look and feel of another project, there will always be a starting point where your page is clean. But even before reaching the starting point, be sure you've given your project a good deal of thought and planning. Work out your graphic approach either in your head or during creative sessions with your client or colleagues. There are strong arguments against drawing on a fresh screen without such foresight and preparation. To get a handle on any multimedia project, you start with pencil, eraser, and paper. Outline your project and your graphic ideas first. Make a flow chart. Storyboard the project using stick figures. Use 3x5 index cards and shuffle them until you get it right. You may not nail it with the first design you submit to a client. Get a few examples from them or have them look at templates from the web. When you have a clear idea what they want, submit a few variations, different visual designs, color palettes, and layouts. Organize your tools. Most authoring systems provide the tools with which you can create the graphic objects of a multimedia: text, interactive buttons, vector-drawn objects, and bitmaps directly on your screen. When you're working with animated objects or motion video, most authoring systems include a feature for activating these elements, such as a programming language or special functions for embedding them. Likely too, your tools will offer a library of special effects, including zooms, wipes, and dissolves. Many multimedia designers do not limit their toolkits to the features of a single authoring platform, but employ a variety of applications and tools to accomplish many specialized tasks. Configure your workspace. When developing multimedia, it is helpful to have more than one monitor to provide lots of screen real estate, viewing area. In this way, you can display the full screen working area of your project or presentation and still have space to put your tools and other menus. This is particularly important in an authoring system such as Flash or Director, where the edits and changes you make in one window are immediately visible in the presentation window, provided the presentation window is not obscured by your editing tool. During development, there is a lot of cutting and pasting among windows and among various applications, and with an extra monitor, you can open many windows at once and spread them out. Both Macintosh and Windows operating systems support this extra hardware. Still images. Still images may be small or large or even full screen. They may be colored, placed at random on the screen, evenly geometric or oddly shaped. Still images may be a single tray on a wintry hillside, stacked boxes of text against a gray, tartan, or Italian marble background, an engineering drawing, a snapshot of your department manager's new BMW. Whatever their form, still images are generated by the computer in two ways, as bitmaps or paint graphics, and as vector drawn or just plain drawn graphics. Bitmaps may also be called raster images. Likewise, bitmap editors are sometimes called painting programs, and vector editors are sometimes called drawing programs. Bitmaps are used for photorealistic images and for complex drawings requiring fine detail. Vector-drawn objects are used for lines, boxes, circles, polygons, and other graphic shapes that can be mathematically expressed in angles, coordinates, and distances. Bitmap versus vector. A drawn object can be filled with color and patterns, and you can select it as a single object. The appearance of both types of images depends on the display resolution and capabilities of your computer's graphics hardware and monitor. What is a bitmap? A bit is the simplest element in the digital world, an electronic digit that is either on or off, black or white, or true or false. This is referred to as a binary, since only two states, on or off, are available. A map is a two-dimensional matrix of these bits. A bitmap, then, is a simple matrix of the tiny dots that form an image and are displayed on a computer screen or printed. Bitmap. A one-dimensional matrix, 1-bit depth, is used to display monochrome images. A bitmap where each bit is most commonly set to black or white. Depending upon your software, any two colors that represent the on and off, 1 or 0 states, may be used. More information is required to describe the shades of gray or more than 16 million colors that each picture element might have in a color image, as illustrated in the figure. These picture elements, known as pulsar, or more commonly pixels, can either be on or off, as in the 1-bit bitmap, or by using more bits to describe them, can represent varying shades of color, 4 bits for 16 colors, 8 bits for 256 colors, 15 bits for 32,768 colors, 16 bits for 65,536 colors, 24 bits for 16,772,216 colors. Thus, with 2 bits, for example, the available zeros and ones can be combined in only 4 possible ways and can then describe only 4 possible colors. What is a pixel? The word pixel means a picture element. Every photograph in digital form is made up of pixels. They are the smallest unit of information that make up a picture. Usually round or square, they are typically arranged in a two-dimensional grid. In the image, one portion has been magnified many times over so that you can see its individual composition in pixels. As you can see, the pixels approximate the actual image. The more pixels you have, the more closely the image resembles the original. Resolution. The number of pixels in an image is sometimes called the resolution. If we are using the term to describe pixel count, one convention is to express resolution as the width by the height. For example, a monitor resolution of 1280 by 1024. This means that there are 1280 pixels from one side to the other and 1024 from top to bottom. Another convention is to express the number of pixels as a single number, like a 5-megapixel camera. A megapixel is a million pixels. This means the pixels along the width multiplied by pixels along the height of the image taken by the camera equals 3 million pixels. In the case of our 1280 by 1024 monitors, it could also be expressed as 1280 by 1020 equals 1,310,720 or 1.31 megapixels. Color information. What is a pixel used for? Each pixel stores color information for your image. It'll usually store it in either 3 components known as RGB, red, green, blue, or 4 components known as CMYK, cyan, magenta, yellow, black. The number of distinct colors that can be represented by a pixel depends on the amount of information stored for each pixel. Information is stored as bits. The more bits per pixel, BPP, that are stored, the more colors a pixel can represent. For example, in the simplest case, if only a single bit of information is stored for a pixel, then it can be on or off, black or white. The actual number of bits used to represent the color of a single pixel is known as color depth or bit depth. Pixel depth. Together, the state of all the pixels on a computer screen make up the image seen by the viewer, whether in combinations of black and white or colored pixels in a line of text, a photograph-like picture, or a simple background pattern. The figure demonstrates various color depths and compression formats. Image 1 is 24 bits deep, millions of colors. Image 2 is dithered to 8 bits using an adaptive palette. The best 256 colors to represent the image. Image 3 is also dithered to 8 bits but uses the Macintosh system palette, an optimized standard mix of 256 colors. Image 4 is dithered to 4 bits, any 16 colors. Image 5 is dithered to 8-bit grayscale, 256 shades of gray. Image 6 is dithered to 4-bit grayscale, 16 shades of gray. And image 7 is dithered to 1 bit, 2 colors, in this case, black and white. Color management. Color is a vital component of multimedia. The next few sections explain where color comes from and how colors are displayed on a computer monitor. Management of color is both a subjective and a technical exercise. Picking the right colors and combinations of colors for your project can involve many tries until you feel the result is right. But the technical description of a color may be expressed in known physical values. Humans, for example, perceive colors with wavelengths ranging from 400 to 600 nanometers on the electromagnetic spectrum. Color models. Understanding natural light and color. Light comes from an atom when an electron passes from a higher to a lower energy level. Thus, each atom produces uniquely specific colors. This explanation of light, known as the quantum theory, was developed by physicist Max Planck in the late 19th century. Niels Bohr, another physicist, later showed that an excited atom that has absorbed energy and whose electrons are moved into higher orbits will throw off that energy in the form of quanta or photons when it reverts to a stable state. This is where light comes from. Color is the frequency of a light wave within the narrow band of the electromagnetic spectrum to which the human eye responds. The letters of the mnemonic ROYG, BIV, learned by many of us to remember the colors of the rainbow, are the ascending frequencies of the visible light spectrum: red, orange, yellow, green, blue, indigo, and violet. Visible spectrum. The visible spectrum is a portion of the electromagnetic spectrum that is visible to, can be detected by the human eye. Electromagnetic radiation in this range of wavelengths is called visible light or simply light. A typical human eye will respond to wavelengths from about 390 to 700 nanometers. In terms of frequency, this corresponds to a band in the vicinity of 430 to 790 terahertz. The spectrum does not, however, contain all the colors that the human eyes and brain can distinguish. Unsaturated colors such as pink or purple variations, such as magenta, are absent, for example, because they can be made only by a mix of multiple wavelengths. Infrared. Infrared IR is electromagnetic radiation with longer wavelengths than those of visible light, extending from the nominal red edge of the visible spectrum at 700 nanometers to 1 mm. This range of wavelengths corresponds to a frequency range approximately 430 terahertz down to 300 gigahertz. Most of the thermal radiation emitted by objects near room temperature is infrared. Ultraviolet UV light. Ultraviolet UV light is electromagnetic radiation with a wavelength shorter than that of visible light, but longer than X-rays, that's in the range of 400 nm and 100 nm, corresponding to photon energies from 3 electron volts to 124 electron volts. It is so named because the spectrum consists of electromagnetic waves with frequencies higher than those that humans identify as a color violet. These frequencies are invisible to most humans except those with aphakia. Near UV is visible to a number of insects and birds. The color white is a noisy mixture of all the color frequencies in the visible spectrum. Sunlight and fluorescent tubes produce white light. Tungsten lamp filaments produce light with yellowish cast. Sodium vapor lamps, typically used for low-cost outdoor street lighting, produce an orange light characteristic of the sodium atom. These are the most common sources of light in the everyday or every night world. The light these sources produce typically reaches your eye as a reflection of that light into the lens of your eye. Which part of our body is used to see? The answer is the eye. Let us see the parts of the eye now. Parts of eye. Cornea. The cornea is a transparent front part of the eye that covers the iris, pupil, and anterior chamber. The cornea with the anterior chamber and lens refracts light, with the cornea accounting for approximately 2/3 of the eye's total optical power. In humans, the refractive power of the cornea is approximately 43 diopters. While the cornea contributes most to the eye's focusing power, its focus is fixed. The curvature of the lens, on the other hand, can be adjusted to tune the focus depending on the object's distance. Medical terms related to the cornea often start with the prefix kerat, from the Greek word horn. The iris, plural, irides or irises, is a thin circular structure in the eye responsible for controlling the diameter and size of the pupil and thus the amount of light reaching the retina. The color of the iris is often referred to as eye color. In optical terms, the pupil is the eye's aperture and the iris is the aperture stop. The pupil. The pupil is a hole located in the center of the iris of the eye that allows light to enter the retina. It appears black because light rays entering the pupil are either absorbed by the tissues inside the eye directly or absorbed after diffuse reflections within the eye that mostly miss exiting the narrow pupil. The crystalline. The crystalline lens is a transparent, biconvex structure in the eye that, along with the cornea, helps to refract light to be focused in the retina. The lens, by changing shape, functions to change the focal distance of the eye so that it can focus on objects at various distances, thus allowing a sharp real image of the object of interest to be formed on the retina. The lens is also known as the aquola, Latin a little stream, of aqua, water, or crystalline lens. In humans, the refractive power of the lens in its natural environment is approximately 18 diopters, roughly 1/3 of the eye's total power. The vertebrate retina. The vertebrate retina, Latin rete, meaning net, is a light-sensitive layer of tissue lining the inner surface of the eye. The optics of the eye create an image of the visual world on the retina through the cornea and lens, which serves much the same function as a film in a camera. Light striking the retina initiates a cascade of chemical and electrical events that ultimately trigger nerve impulses. These are sent to various visual centers of the brain through the fibers of the optic nerve. The optic nerve, also known as cranial nerve 2, transmits visual information from the retina to the brain. Light passes through the pupil. This is a central circular opening in the colored part of the eye, also called the iris. Depending on how much light there is, the iris may contract or dilate, limiting or increasing the amount of light that gets deeper into the eye. The light then goes through the lens, Just like the lens of a camera, the lens of the eye focuses the light. The lens changes shape to focus on light reflecting from near or distant objects. This focused light now beams through the center of the eye. Again, the light is bathed in moisture, this time in a clear jelly known as vitreous. Surrounding the vitreous is the retina. Light reaches its final destination in the photoreceptors of the retina. The retina is the inner lining of the back of the eye. It's like a movie screen or the film of a camera. The focused light is projected onto its flat, smooth surface. Signals sent from the photoreceptors travel along the nerve fibers to a nerve bundle which exits the back of the eye. The bundle is called the optic nerve. The optic nerve sends the signals to the visual center in the back of the brain. Here it's interpreted. Now light reflected from an object has entered the eye, been focused, converted into electrochemical signals, delivered to the brain and interpreted or seen as an image. Primary colors: red, yellow, and blue. In traditional color theory, these are the three pigment colors that cannot be mixed or formed by any combination of other colors. All other colors are derived from these three hues. Secondary colors: green, orange, and purple. These are the colors formed by mixing the primary colors. Tertiary colors: yellow-orange, red-orange, red-purple, blue-purple, blue-green, and yellow-green. These are the colors formed by mixing one primary and one secondary color. Color harmony. Harmony can be defined as a pleasing arrangement of parts, whether it be music, poetry, color, or even an ice cream sundae. In visual experiences, harmony is something that is pleasing to the eye. It engages the viewer and it creates an inner sense of order, a balance in the visual experience. When something is not harmonious, it's either boring or chaotic. At one extreme is a visual experience that is so bland that the viewer is not engaged. The human brain will reject understimulating information. At the other extreme is a visual experience that is so overdone, so chaotic that the viewer can't stand to look at it. The human brain rejects what it cannot organize, what it cannot understand. The visual task requires that we present a logical structure. Color harmony delivers visual interest and a sense of order. In summary, extreme unity leads to understimulation. Extreme complexity leads to overstimulation. Harmony is a dynamic equilibrium. A color scheme based on analogous colors. Analogous colors are any three colors which are side by side on a 12-part color wheel, such as yellow-green, yellow, and yellow-orange. Usually one of the three colors predominates. Complementary colors are any two colors which are directly opposite each other, such as red and green, and red and purple, and yellow-green. In the illustration above, there are several variations of yellow-green in the leaves and several variations of red-purple in the orchid. These opposing colors create maximum contrast and maximum stability. A color scheme based on nature. Nature provides a perfect departure point for color harmony. In the illustration above, red, yellow, and green create a harmonious design, regardless of whether this combination fits into a technical formula for color harmony. Color context. How color behaves in relation to other colors and shapes is a complex area of color theory. Compare the contrast effects of different color backgrounds for the same red square. Red appears more brilliant against a black background and somewhat duller against a white background. In contrast with orange, the red appears lifeless. In contrast with blue-green, it exhibits brilliance. Notice that the red square appears larger on black than on other background colors. Different readings of the same color. If your computer has sufficient color stability and gamma correction, you will see that the small purple rectangle on the left appears to have a red-purple tinge when compared to the small purple rectangle on the right. They are both the same color as seen in the illustration below. This demonstrates how three colors can be perceived as four colors. Observing the effects colors have on each other is a starting point for understanding the relativity of color. The relationship of values, saturations, and the warmth or coolness of respective hues can cause noticeable differences in our perception of color. Color palettes. Palettes are mathematical tables that define the color of a pixel displayed on the screen. The most common palettes are 1, 4, 8, 16, and 24 bits deep. In computer graphics, a palette is either a given finite set of colors for the management of digital images, that is a color palette, or a small on-screen graphical element for choosing from a limited set of choices, not necessarily colors, such as Tools palette. When color monitors became available for computer, managing the computations for displaying colors severely taxed the hardware and memory available at the time. 256 color 8-bit images using a color lookup table or palette were the best a computer could do. In 24-bit color systems, your computer works with 3 channels of 256 discrete shades of each color, red, green, and blue, represented as the 3 axes of a cube. This allows a total of 16,777,216 colors, 256 into 256 into 256. Dithering. If you start out with a 24-bit scanned image that contains millions of colors and need to reduce it to an 8-bit 256 color image, you get the best replication of the original image by dithering the colors in the image. Since there are now only 256 colors available to represent the thousands or even millions of colors in the original image, pixels using the 256 remaining colors are intermixed and the eye perceives a color not in the palette, created by blending the colors mixed together. Dithering is a process whereby the color value of each pixel is changed to the closest matching color value in the target palette using a mathematical algorithm. Often the adjacent pixels are also examined and patterns of different colors are created in the more limited palettes to best represent the original colors. Thus, any given pixel might not be mapped to its closed palette entry, but instead to the average over some area of the image. This average will be closer to the correct color than a substitute color would be. How well the dithered image renders a good approximation of the original depends upon the algorithm used. Image compression. Now let us see what image compression is. All data types, text, numbers, images, video, sound, etc. can be compressed. In some applications, it is imperative that a compressed document must be exactly the same as the original when it is uncompressed, and in others, some loss of information is acceptable. For example, if you compress a program or a payroll file, you must get an exact copy of the original when it is uncompressed. On the other hand, it is not necessary that an image or song be exactly the same when uncompressed. Compression that keeps all information is called lossless, and compression in which some information loss is tolerable is called lossy. Lossy compression is usually acceptable for images. What's this image compression thing? Image compression is used to minimize the amount of memory needed to represent an image. Images often require a large number of bits to represent them, and if the image needs to be transmitted or stored, it is impractical to do so without somehow reducing the number of bits. The problem of transmitting or storing an image affects all of us daily. Compression ratio is defined as the ratio of an original image and compressed image. Compression ratio equals original image size by compressed image size. Image compression coding is to store the image into bit stream as compact as possible and to display the decoded image in the monitor as exact as possible. Now consider an encoder and a decoder as shown in the figure. When the encoder receives the original image file, the image file will be converted into a series of binary data, which is called the bitstream. The decoder then receives the encoded bitstream and decodes it to form the decoded image. If the total data quantity of the bitstream is less than the total data quantity of the original image, then this is called image compression. The full compression flow is as shown in figure. Why an image can be compressed? The reason is that the correlation between one pixel and its neighbor pixels is very high, or we can say that the values of one pixel and its adjacent pixels are very similar. Once the correlation between the pixels is reduced, we can take advantage of the statistical characteristics and the variable length coding theory to reduce the storage quantity. This is the most important part of the image compression algorithm. There are a lot of relevant processing methods being proposed. Image compression, JPEG, seen most often with the .jpeg extension, is a commonly used method of lossy compression for digital images, particularly for those images produced by digital photography. The degree of compression can be adjusted, allowing a selectable trade-off between storage size and image quality. JPEG compression is used in a number of image file formats. JPEG EXIF is the most common image format used by digital cameras and other photographic image capture devices. Along with JPEG, JFIF, it is the most common format for storing and transmitting photographic images on the World Wide Web. These format variations are often not distinguished and are simply called JPEG. The term JPEG is an acronym for the Joint Photographic Experts Group, which created the standard. The JPEG compression algorithm is at its best on photographs and paintings of realistic scenes with smooth variations of tone and color. On the other hand, JPEG may not be as well suited for line drawings and other textual iconic graphics, where the sharp contrast between the adjacent pixels can cause noticeable artifacts. Such images may be better saved in a lossless graphics format, such as TIFF, GIF, PNG, or a raw image format. As a typical use of JPEG is a lossy compression method, which somewhat reduces the image fidelity, it should not be used in scenarios where the exact reproduction of the data is required, such as some scientific and medical imaging applications and certain technical image processing work. JPEG uses a lossy form of compression based on the discrete cosine transform. This mathematical operation converts each frame of the space domain into the frequency domain. A perceptual model based loosely on the human psychovisual system discards high-frequency information, like sharp transitions in intensity and color hue. In the transform domain, the process of reducing information is called quantization. In simpler terms, quantization is a method for optimally reducing a large number of scale with different occurrences of each number into a smaller one, and the transform domain is a convenient representation of the image because high-frequency coefficients, which contribute less to the over picture than other coefficients, are characteristically small values with high compressibility. The quantized coefficients are then sequenced and losslessly packed into the output bit stream. Simpler explanation. JPEG compression starts by breaking the image into 8 by 8 pixel groups. The full JPEG algorithm can accept a wide range of bits per pixel, including the use of color information. In this example, each pixel is a single byte, a grayscale value between 0 and 255. These 8 by 8 pixel groups are treated independently during compression. That is, each group is initially represented by 64 bytes. After transforming and removing data, each group is represented by, say, 2 to 20 bytes. During uncompression, the inverse transform is taken of the 2 to 20 bytes to create an approximation of the original 8 by 8 group. These approximated groups are then fitted together to form the uncompressed image. JPEG 2000. JPEG 2000 is an image compression standard and coding system. It was created by the Joint Photographic Experts Group Committee in 2000 with the intention of superseding their original discrete cosine transform-based JPEG standard created in 1992 with a newly designed wavelet-based method. While there is a modest increase in compression performance of JPEG 2000 compared to JPEG, the main advantage offered by JPEG 2000 is the significant flexibility of the code stream. The code stream obtained after compression of an image with JPEG 2000 is scalable in nature. By ordering the code stream in various ways, applications can achieve significant performance increases. However, as a consequence of this flexibility, JPEG 2000 requires encoders, decoders that are complex and computationally demanding. Image file formats, GIF. The Graphics Interchange Format, better known by its acronym GIF, is a bitmap image format that was introduced by CompuServe in 1987 and has since come into widespread usage on the World Wide Web due to its wide support and portability. The format supports up to 8 bits per pixel for each image, allowing a single image to reference its own palette of up to 256 different colors chosen from the 24-bit RGB color space. It also supports animations and allows a separate palette of up to 256 colors for each frame. These palette limitations make the GIF format unsuitable for reproducing color photographs and other images with continuous color, but it's well suited for simpler images such as graphics or logos with solid areas of color. GIF images are compressed using the Lempel-Welch lossless data compression technique to reduce the file size without degrading the visual quality. This compression technique was patented in 1985. Portable Network Graphics. Portable Network Graphics (PNG) is a raster graphics file format that supports lossless data compression. PNG was created as an improved, non-patented replacement for graphics interchange format GIF and is the most used lossless image compression format on the Internet. PNG supports palette-based images, grayscale images, and full-color non-palette-based RGB images. PNG was designed for transferring images on the Internet, not for professional quality print graphics, and therefore does not support non-RGB color spaces such as CMYK. Difference between JPG, PNG, and GIF files. BMP bitmap. This was probably the first type of digital image format. This is generally medium-high quality but produces larger file sizes. This format is ideal for icons and small images. JPG, JPEG became popular with the invention of the digital camera. High-quality images and huge compression allows for big resolutions but small file sizes. This is the most common image format, especially for photos. GIF. This format was created mainly for Internet uses, mainly for its small file size. It's good for fast-loading web pages only. PNG. Portable Networks Graphic. They're the best overall image format, especially for computer-generated graphics and files containing text and images, having sharp transitions, but not as good as JPEGs for photos because of the larger file size. Although not as compatible with the Windows operating systems as other formats, PNGs produce very high-quality images with high resolution. JPG, GIF, and PNG in short. PNG is a good option for transparency and non-lossy smaller files. Larger files, not so much unless you demand non-lossy images. GIF is largely a novelty and only useful for animation but can produce small 8-bit images. JPG is still the king for photographs and photo-like images on the Internet, but be careful as your file can degrade with every save. TIFF or TIFF. TIFF is a computer file format for storing raster graphics images, popular among graphic artists, the publishing industry, and both amateur and professional photographers in general. The format was originally created by the company Aldus for use in desktop publishing. The specification originally had the name TIFF as the acronym for Tagged Image File Format. TIFF is a flexible, adaptable file format for handling images and data within a single file by including the header tags, size, definition, image data arrangement, applied image compression, defining the image's geometry. A TIFF file, for example, can be a container holding compressed lossy JPEG and lossless PACBits compressed images. The ability to store image data in a lossless format makes a TIFF file a useful image archive because unlike standard JPEG files, a TIFF file using a lossless compression or none may be edited and resaved without losing image quality. EXIF, Exchangeable Image File Format, officially EXIF, not EXIF according to JEIDA, JEITA, CIPA specifications, is a standard that specifies the formats for images, sound, and ancillary tags used by digital cameras, including smartphones, scanners, and other systems handling image and sound files recorded by digital cameras. The specification uses the following existing file formats with the addition of specific metadata tags. JPEG Discrete Cosine Transform for compressed image files, TIFF, revision 6.0, RGB or YCBCR for uncompressed image files, and RIF-WAVE for audio files, Linear PCM or ITU, TG.711 U-Law PCM for uncompressed audio data, and IMA AD-PCM for compressed audio data. It is now supported in JPEG 2000, PNG or GIF. PS file format. PostScript PS is a computer language for creating vector graphics. It is a dynamically typed, concatenative programming language. Image saved in the PostScript page description language may contain vector graphics, raster graphics, and text. Can be printed directly by a PostScript printer containing a raster image processor without being opened in an application. PDF file format. Portable document format, PDF, is a file format used to present documents in a manner independent of application software, hardware, and operating systems. Each PDF file encapsulates a complete description of a fixed layout flat document, including the text, fonts, graphics, and other information needed to display it. EPS, Encapsulated PostScript, is another print industry standard format that's been around for quite a while, but its use has been in decline over the years. EPS files are not really image files in the traditional sense. Instead, they contain a series of instructions for how a printer should reproduce the image. They can be imported into most page layout programs, but the encapsulated part means the files are essentially locked and can no longer be modified unless they are reopened in Photoshop. A preview image must be embedded in the EPS file when you save it in Photoshop if you want it to be viewable on screen when working in your page layout program. Otherwise, you won't be able to see it until the layout is printed. While EPS remains an industry standard format, you probably won't use it very often unless it's the format specifically requested by your commercial printer. JPEG versus TIFF versus PDF. JPEG is a lossy format, only useful for things you don't want to edit or only want low-quality versions of. TIFF can be lossless or lossy depending on the compression options you choose and is appropriate for image data. PDF can be lossless or lossy depending on the compression options you choose and is appropriate for text or complex documents, mixed text and images. Basic image processing using Photoshop. Set the depth. In Photoshop Elements, choose File Open and browse to start image. The image is a digital negative, so it will open an Adobe Camera Raw. To squeeze as much color and tonal information out of the file as possible, set the depth drop-down menu to 16 bits per channel. Set the white balance. The shot's mountains look a little too warm. Because it's a raw file, you can cool things down easily by dragging the temperature slider left to 4900. You can counteract the image's slightly green hue by dragging tint right to -1. This creates a custom white balance setting. Analyze the exposure. The histogram helps you spot any exposure problems. The histogram graph fails to stretch to the far left, so we can see that the shot lacks strong, dark shadows. The graph's highlights drop off before they reach the far right, too, which means that the image consists mostly of midtones. Reveal texture. The shot's contrast is a little flat. To give it more impact, we need to darken the shadows and brighten the highlights. This will help us to reveal more texture and detail in the mountains and surrounding landscape. Drag exposure to +0.25. This gives the shot stronger highlights. Use of image editing software. To get the best out of any image requires processing in an image editing package. Now that we see how the Photoshop package works, let us apply the techniques. In this set of instructions, we will show how a raw image and explain the processing applied in Adobe Photoshop. This image is the original raw file prior to any post-processing. This layer was then adjusted for levels, making the dark clouds blacker and the highlights a little lighter without blowing the detail. Now the sky layer colors were adjusted using the color balance tool. The midtones had the red increased by 15, the highlights had the yellow reduced by -17, and the shadows 1 increased the blue by 19. Select the background layer. Once again, we need to adjust the levels to maximize the contrast in the image again, ensuring you don't clip the highlights or fill the shadows. Once you're happy with the levels, the background layer also needs the color balance changing. Again, increase the red in the midtones, reduce the yellow in the highlights, and increase the blue in the shadows. Now flatten the layers and adjust the levels to provide the image you had in your imagination. Finally, and this is always the final operation, sharpen the image. Please note, you should never sharpen an image until all processing is complete and you've resized to the final image size. It's always worth keeping an unsharpened copy in case you want to produce a bigger version at a later date. Color balance software. In photography and image processing, color balance is a global adjustment of intensities of the colors, typically red, green, and blue primary colors. An important goal of this adjustment is to render specific colors, particularly neutral colors, correctly. Hence, the general method is sometimes called gray balance, neutral balance, or white balance. Color balance changes the overall mixture of colors in an image and is used for color correction. Generalized versions of color balance are used to get colors other than neutrals to also appear correct or pleasing. White balance. Sometimes the white balance in your image is right on, and other times it's miles off. Don't worry, it happens to all of us, and it's easy to fix. To begin, we locate the black point in the sample image. Locate and set the black point. Open the image in Photoshop and set the image mode to 16 bits by selecting Image, Mode, 16 bits, Channel. Setting your image to 16 bits is optional, but I always work in 16-bit mode to minimize information loss. Click on the Create a New Fill or Adjustment Layer icon and select Threshold. In the Threshold dialog box, move the adjustment slider all the way to the left. Next, slowly drag the adjustment slider back to the right until black areas begin to appear in the image. Once you've identified some blacks in the image, select the Color Sampler tool. If you don't see this tool, click and hold on the eyedropper tool, and in the resulting submenu, select the Color Sampler tool. Using the Color Sampler tool, click once in the area that you determined to be black to set the color sampler point. If you happen to miss the spot you were trying to click on, you can drag the point you placed to the correct location by clicking and holding your mouse button down on the point while you drag. The next step is to create a curves layer that will contain this black point. Click on the curves icon on the adjustment panel or use the main menu and select Layer, New Adjustment Layer, Curves. After deleting the threshold layer, make the upper layer active again by clicking once on it. The curves layer. In the curves dialog box, you will see 3 eyedropper icons from top to bottom. They represent the black point, the gray point, and the white point. Because we are setting the white point in this step, click once on the black point eyedropper icon to select it. Next, locate the color sampler point we created earlier and click once directly on it to set the black point. When you do this, you will probably notice that the curve shown in the curves dialog box has changed to reflect the white point change. Dynamic range correction. Dynamic range in photography describes the ratio between the maximum and minimum measurable light intensities, white and black respectively. In the real world, one never encounters true white or black, only varying degrees of light source intensity and subject reflectivity. Therefore, the concept of dynamic range becomes more complicated and depends on whether you are describing a capture device, such as a camera or scanner, a display device, such as a printer or computer display, or the subject itself. Dynamic range correction tones down bright areas in order to reduce the chance of blown highlights. 4 settings are available: Off, the factory default; Auto, 200% and 400%. The Auto setting can be used over the full range of ISO numbers, but the 200% and 400% settings are restricted to ISO ranges of 160 to 1600, 320 to 1600, respectively. Gamma encoding of images is required to compensate for properties of human vision, hence to maximize the use of the bits or bandwidth relative to how humans perceive light and color. Human vision under common illumination conditions, not pitch black, nor blindingly bright, follows an approximate gamma or power function. If images are not gamma encoded, they allocate too many bits or too much bandwidth to highlights that humans cannot differentiate, and too few bits or bandwidth to shadow values that humans are sensitive to and would require more bits bandwidth to maintain the same visual quality. Photo retouching, photo manipulation, also called photoshopping or before the rise of Photoshop software, airbrushing, is the application of image editing techniques to photographs in order to create an illusion or deception in contrast to mere enhancement or correction after the original photographing took place. Recap: planning your approach, organizing your tools, and configuring your computer workspace. What you see on a multimedia computer screen is the viewer's primary connection to all of your project's content. Work out your graphic approach before you begin, either in your head or during creative sessions with your client or colleagues. To get a handle on any multimedia project, start with pencil, eraser, and paper. Differentiate among bitmap and vector images. Bitmaps are an image type most appropriate for photorealistic images and complex drawings requiring fine detail. Vector images are most appropriate for lines, boxes, circles, polygons, and other graphic shapes that can be mathematically expressed in angles, coordinates, and distances. Use of colors and palettes in multimedia. Color is the frequency of light wave within the narrow band of the electromagnetic spectrum to which the human eye responds. Different cultures associate certain colors with different meanings. For 8-bit GIF images, the computer uses a palette of 256 colors to determine which colors to display. Dithering is a process whereby the color value of each pixel is changed to the closest matching color value in the target palette. Various file types used in multimedia. GIF and PNG images use palettes of colors. Windows uses device-independent bitmaps, DIBs, as its common image file format, usually written as BMP files. TIFF, or Tagged Interchange File Format, was designed to be a universal bitmapped image format and is also used extensively in desktop publishing packages. For handling drawn objects across many platforms, there are two common formats, DXF and IGS. JPEG and GIF images are the most common bitmap formats used on the web and may be considered cross-platform, as all browsers will display them. Conclusion. In this chapter, the users have covered the following aspects of image fundamentals and representations: color science, color models, color palettes, dithering, 2D graphics, image compression and file formats, GIF, JPEG, JPEG 2000, PNG, TIFF, EXIF, PS, PDF. Basic image processing, use of image editing software, white balance correction, dynamic range correction, gamma correction, photo retouching.